Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss the topic. So let me write it down. It is distribution of energy between systems in equilibrium. Distribution of energy between systems in equilibrium. So this is our today's topic. Let me adjust it. No, do it separate. No, let me correct it first. I think I should write it. Okay, let me first get my pen back. First, I will encircle it. Let me get my pen back. There is my pen. So let us move. Distribution of energy between systems in equilibrium. So it is our today's topic. Actually, we have discussed the content of this lecture in the classroom in the offline mode through an example at the start of the course in the classroom. Today we are going to discuss the same thing more rigorously. So in the last lecture, we discussed the idea of thermal interaction between two macroscopic systems, A and A prime. So they are two macroscopic systems. As I told you in the last lecture, macroscopic system means that its number of degrees of freedom is large. So today we are going to talk about this thermal interaction between these two macroscopic systems, A and A prime, in detail. So we denote the respective energies of these systems by E and E prime. So E is the energy of system A, and E prime is the energy of system A prime. Okay, then what we imagine? We imagine that the energy scales be subdivided into equal small intervals of respective magnitudes delta E and delta E prime. So we divide the energy scale pertaining to system A into small equal intervals delta A, and in case of system A prime, our small equal intervals in energy are delta E prime, right? Again, let sigma of E be the number of states of A. When I say A, that is system A. So number of states of system A in the range between E and E plus delta E. And let me get to the next page. Sigma prime of E prime is the number of states of system A prime in the range between in the range between E prime and E prime plus delta E prime. So it is very essential to define the symbols you use. So we define this way. Now we assume that the systems are not thermally isolated from each other, as we discussed in the last lecture, so that they are free to exchange energy, and we assume the external parameters of the systems are fixed. Thus the energy transfer is in the form of heat. Now the combined system, let me write it. The combined system we denote by A naught, which is the sum of these two systems, that is A plus A prime. This combiner system is isolated. So this combiner system is isolated, and its total energy we denote by E naught superscript naught is therefore constant, right? Because it is isolated. Now the energy of each system separately, that is A and A prime, is however not fixed, since A and A naught, sorry, not A, I am talking of A and A prime. A naught is the combined system that is isolated. Its total energy is E naught, which is constant. Now, the systems A and A prime, now they are the subsystems of the total system. They can exchange energy. Therefore, energy of A and A prime is not fixed, right? Now we can write E plus E prime equal to E naught, and then E naught is constant. Let me name it first, and let me encircle this equation. So it is simply as we discussed in the last lecture, the conservation of energy statement. So we can write E plus E prime is equal to E naught, and that is constant. But remember, in this equation 1, we are assuming that the interaction between systems A and A prime is weak. Assuming the interaction, which is thermal interaction, between A and A prime is weak. Think about this. This is the assumption in writing equation 1, right? Now suppose that these systems A and A prime are in equilibrium with each other, and focus attention on a representative ensemble which we discussed in the last lecture. Then the energy of A can assume a large range of possible values, but these values occur by no means with equal probability. Suppose that the system A has an energy E, which is more precisely between E and E plus delta E, then the corresponding energy of A prime by equation 1 is known to be, we can write E prime is equal to E naught minus E. I name this second. Let me encircle it simply. Right? You can write the if the energy of the system A is E or near E, then we can write the energy of A prime as E naught minus E. Now the number of states accessible to the entire system A naught can thus be regarded as a function of a single parameter, that is energy E of the system A, right? Because when system A has energy E, system A prime has energy E naught minus E, E naught is fixed, right? So the combiner system, number of states accessible to the combiner system A naught can be regarded as a function of single parameter, that is energy E of system A. This is obvious because the only parameter here becomes then E when you express E prime in terms of equation 2. Now we denote by sigma naught of E. What is it? It is the number of states accessible to the combiner system A naught when A has an energy between E and E plus delta E. Understand it? We are expressing the number of states accessible to the combiner system in terms of the energy which system A can acquire, because it becomes the variable when we express E prime using equation 2. So sigma naught of E is now number of states accessible to combiner system A naught when A has an energy between E and E plus delta E. Now the averaging postulate, which is the fundamental postulate, asserts that in equilibrium, A naught must be equally likely to be found in any one of its states. Why so? Because it is isolated, right? So hence it follows that, let me first define another symbol. If P of E is the probability of finding combiner system A naught in a configuration or in a state, that is one and the same thing, in a state or configuration where A has an energy between E and E plus delta E. So if P of E is denoting this probability for the combiner system to be in a state where A has an energy between E and E plus delta E, then this probability is simply proportional to the number of states accessible to the total system A naught under these circumstances. That is, we can write P of E is equal to C sigma naught of E. To understand it, we're talking about the probability for the combined system in terms of the energy possessed by the subsystem A, that is E, which we can do because we are specifying the states of the combined system in terms of the states of the system A, right? Where C is a constant of proportionality, proportionality, independent of E, independent of energy E. So let me encircle it. This is my equation 3. Now we can see how this probability function P of E behaves with the variation in E. I will give you its graph, but that graph can be mathematically justified. This P of E, when we plot with E, see how it varies with E. Let me try to make it neat. This P of E will have a sharp peak. It will have a sharp peak at some value of energy. We call that energy as E curly, right? I will give you here home assignment. Justify this graph mathematically at home. That means you have to check how this comes about using this equation 3 or other equations which we have written, right? So it has a sharp peak. It peaks at some value of energy which we name E curly. Now we want to locate the position of the maximum of P of E, or equivalently of the maximum of its logarithm. So we need to find the value of E equal to E curly, where the partial derivative of ln P versus energy, which is equal to 1 over P dou P by dou E. We have to equate it to 0. I call it an equation. How many equations we have written? We missed an equation. Okay, I will write that. Let me name it first, this equation, as equation 4. I name it equation 4. This is my equation 4. So what is the idea? Idea is we have first expressed this probability function using equation 3 in terms of the total states accessible to the combiner system. Then we said this P of E has a sharp peak at some energy E equal to E curly. Then I told you we need to find its maximum. So for that, what we can do, we have to maximize P or ln P. So we can find the partial derivative of ln P versus E, which is 1 by P dou P by dou E, and equate it to 0. Now to do this, we need to first figure out what is ln P now. For that, we need to understand one thing. I can write sigma naught of E. What is that? That is the total states accessible to combiner system as the product of sigma of E times sigma prime of E naught minus E. Let me name it 5. Let me justify it. See, when A has an energy E, it can be in any one of its sigma E states, right? At the same time, A prime must then have an energy E prime equal to E naught minus E, so that it can be in any one of its states, that is sigma prime of E prime, which is sigma prime of E naught minus E, possible states. Now, since every possible state of A can be combined with every possible state of A prime to give a different state of the total system A naught. Therefore, the number of distinct states accessible to the combiner system A naught when A has an energy E is simply given by this equation 5. Understand it. This is the number of states accessible to system A, right? This is the number of states accessible to system A prime, right? This is the number of states accessible to the combiner system A naught, my left hand side. You can express this as product of these two, right? Because as I told you, every possible state of A can be combined with every possible state of A prime to give a different state of the total system A naught, right? So because of that, we can write equation 5. This E naught minus E is actually E prime, right? So this is my equation 5. Therefore, how I can use this 5 in equation 3? Using 5 in 3, what we get? Using equation 5 in equation 3, what we get? We get P of E is constant of proportionality times sigma of E times sigma prime of E naught minus E. Let me name it. This is my sixth equation. P of E is C times sigma of E times sigma prime of E prime, which is E naught minus E. What we have done, we have used 5 in 3. This is my 5. This is my 3. So I replace it here sigma naught of E by the product of these two factors. So I got this equation 6. What we want ln of P, so that we can put that in equation 4. So let us find. So what is my ln of P then? When I apply logarithm to this equation, my ln of P of E is simply, this product will become sum ln of C plus ln of sigma of E plus ln of sigma prime of E prime. Let me name it equation 7. So ln of P of E is ln of C plus ln of sigma of E plus ln of sigma prime of E prime, because this is here E prime inside the bracket, right? Now we have to use equation 6, not 6. I should write using 7 in 4 using 7 in 4, equation 7. Let me get the pen back. Using equation 7 in equation 4. 4 is the condition for maximization. Now we are using expression 6 for ln of p. Expression 7 using 7 in equation 4. Right? That is 4. This is 7. When I do it, what I get? I get dou by dou E of ln of sigma of E plus dou by dou E prime of ln of sigma prime of E prime times minus 1 is equal to 0. I name it equation 8. What is it? Dou by dou E of ln of sigma of E plus dou by dou E prime of ln of sigma prime of E prime minus 1 is equal to 0. See what we have done when you find the derivative of this equation 7 with E. Partially you differentiate it with respect to E when you are putting it in this equation 4. You have to put it ln P here and differentiate it with respect to E and equate that to 0. This first term will go out, it will be 0. Then this is your first term, ln dou by dou of E of ln sigma of E. Then this is second term. But see what we have done. I have actually changed here the variable with which I am differentiating. I am differentiating with respect E prime, not E. But I have multiplied here by minus 1. I will give you this to think or check. So I will write here, check it. Check this. So this equation 8 is now what? It is the condition for P of E to be maximum. We're finding that peak using this equation. Now what we do, we define here a parameter. You already know that. I write it or beta of E curly is equal to beta prime of E prime curly. That's what my equation 8. I call it 9. Where E curly and E prime curly denote the corresponding energies of A and A prime at the maximum, which we are figuring out. And we have defined a parameter beta, which is function of E, as the partial derivative of ln of sigma with E. I name it, let me do one thing. Okay, no issue. I name it 10. So this defines your beta. So we're defining beta of E as the partial derivative of ln sigma with E. So this equation 8 is then equation 9, because this becomes beta pertaining to system A. This becomes, when you take it to the right hand side, it becomes positive. That becomes beta prime, which we have written. But at the energy E curly, where the probability of E or ln of that maximizes, right? Now C, accordingly, there will be what? Beta prime of E. What will be beta prime of E? That will be, beta prime of E will be, that will be beta prime of E prime. That will be what? Dou by dou E prime of ln of sigma prime. That is this, right? When you take it to the right hand side, it becomes positive. So we have written this way. So this maximization condition we have written in terms of equation 9, right? Now this beta, you can see, has by definition the dimensions of reciprocal energy, because from 10 in the denominator you have energy, in the numerator you have just number, so its dimensions will be reciprocal energy. And we define it this way. We have discussed it already. KT, T is the thermodynamic temperature, and we now know K is the Boltzmann constant, is 1 over beta, right? Let me name it 11, right? Now using this definition of beta and connecting it to the temperature this way through equation 11, you can see by equation, let me check the number, by equation 10, by equation 10, which is defining beta as a partial derivative, I can write 1 by T is equal to partial of S with respect to energy, where, let me name it 12, where S is K ln sigma. Let me name it 13. I'm saying by equation 10, I can write 1 by T as dou S by dou E, right? Where S is K ln sigma. right? You can check it. This quantity S, as we have discussed already throughout, it has a name. It is called entropy. Now the condition for maximum probability P of E is then by equation, let me check the equation number. This equation, what is the number here? This equation 7, this one, by equation 7 expressed as the condition that the total entropy S plus S prime, S is the entropy of system A, S prime is the entropy of uh, uh, A prime system, and the sum is the total entropy of the whole combiner system is maximum. Let me name this equation 14. And that condition occurs by equation, what is the number? By equation 9, by equation 9, when T is equal to T prime, where T is the temperature of system A and T prime is the temperature of system A prime. Now you need to check this, what I have written here. Check this. I'm saying the condition that probability is maximum translates into this condition by equation 7, that the total entropy of the combined system is maximum, and that occurs when the temperatures of the two subsystems, they are thermodynamic temperatures of the two subsystems A and A prime, are equal. Now before leaving you, I need to first our topic was distribution of energy between systems in equilibrium. So we said let there be two macroscopic systems and A prime. Let E be energy of system A, E prime be energy of system A prime, and the energy scale of E be divided into small equal intervals delta E and delta E prime pertaining to another system. Then sigma E was the number of states of A in the energy range between E and E plus delta E. Similarly, we defined sigma prime of E prime. Then the combined system was A naught. Its total energy is constant because that is isolated, and we are assuming the interaction between A and A prime is weak, so we can write total energy as the sum of the energies of the two subsystems. Then we said we can write the number of states accessible to the combiner system when A has an energy between E and E prime. We can connect it with the probability of finding the combiner system in a state where A has an energy between E and E plus delta E. We wrote this proportionality, then C is constant. Then we said this probability function has a maximum, which I gave you the assignment, check it mathematically at an energy E curly. Then to find that maximum, we said we will take its logarithm and equate the derivative of that with respect to energy to 0. So maximum condition is equation 4. Then we said I can write this sigma naught E as product of these two factors. Then we found this P of E, then ln, then we find this derivative. Here we change the variable of integration. Sorry, not variable of integration, variable with which we are differentiating. We define beta. Then we define beta in terms of temperature, because we said its dimensions must be reciprocal of energy. We have already defined beta, but I have to point one thing. I will tell you one thing. Then I told you by equation 10, I can write it this way, 1 by T this way, where S is entropy, which is K ln sigma. You will check that. Then I said that the probability maximum means the total entropy is maximum, and that occurs when the temperatures of the two subsystems are equal. Now let us justify our topic. Idea was, see, we have two subsystems, A and A prime. A contains some energy and A prime contains some energy. Now we bring them in thermal contact. Overall combined system is isolated. So whatever energy is in the two systems, that is there. That is fixed, which is E naught. We wanted distribution of energy. We wanted to understand how this total energy between two subsystems is distributed among these systems. So what we learned that heat will transfer between two subsystems until this probability function is maximized, or until the entropy of the total system becomes maximum. And that occurs when their temperatures become equal. So energy is distributed in the combiner system to maximize the total entropy that occurs when their temperatures are equal. So this was the crux of the topic. Another thing I need to tell you, in the previous lectures till now, we have defined beta. Let me write it in red here. We have defined beta as minus 1 over kT or kBT, but here we are defining it as 1 by kT, not minus. We are not including minus in it. So that's not important. Important is you can do this way also. You can take beta, you don't take minus inside, but you have to accordingly make adjustments in your expressions. So some books absorb the minus inside the definition of beta, some take it positive, but they have to put that minus then in the coming expressions, adjust accordingly the minus sign. So I did it deliberately today without minus, so that you can uh, understand how things are being uh, manipulated, written, understood. So that's not important. Important is whatever symbols, whatever you write, you need to define your symbols and understand what you are doing. So this is all for today. Thank you. Do not forget to like, share, and subscribe my channel. Assalamu alaikum.